All right, so as a corollary of the corollary, let G with the operation star be a group. And for every pair of elements in the set G, the inverse of the quantity A star B is B inverse star A inverse. Now, if the group is abelian, then the order does not matter. But if we have a non-commutative group, then order does matter. All right, so proof. Let A and B be in the set G. Then as G is a group, it is a magma, so it's closed into the operation. And so A star B is also an element in the group. So there exists a unique inverse quantity A star B inverse in the set G, such that quantity A star B inverse star A star B, quantity A star B, is equal to the identity element. Now, as the element B is in the set G, and this is a group, there exists an inverse for that element, and so we can perform the operation on the right with the inverse of B. So A, quantity A star B inverse star A star B inverse is equal to E star B inverse. Now, as we are in a group, the operation is associative, and so we can group the terms any way we like. And so now we have A star B inverse star A star identity is B inverse. And more simply, quantity A star B inverse star A is equal to B inverse. Now, as the element A is in the group, there exists an inverse for that element, and so we can perform the operation star on the right with the inverse of A. So quantity A star B inverse star A inverse is equal to B inverse star A inverse. Again, in a group, the operation is associative, and so we can group the terms any way we like. And so we have quantity A star B inverse star identity is B inverse star A inverse. Or more simply, quantity A star B inverse is B inverse star A inverse. All right? So next we'll prove a theorem. Let G together with some operation star be a group. And let the elements A and B be in the group. Then the linear equations A star X equals B and Y star A equals B have unique solutions X and Y in the group. All right, the proof for this theorem is very simple, but this is perhaps one of the most important theorems that we will look at. First of all, notice that in a group, a linear equation consists of a single operation. But this theorem states that in a group, a linear equation with coefficients in the set, underlying set in the group, will have a unique solution that is also in the group. So also notice that this statement, the statement of the theorem, is an existence and uniqueness statement. That is, not only does a solution exist, but that solution is unique. And so to prove this theorem, we will first show that there exists at least one solution, and then show that that solution is unique. So first statement, we have that A star X is equal to B. Now, as we are in a group, for each element, the inverse exists. And so we can perform the operation star on the left with the inverse of A. And so we have A inverse star A star x is A inverse star B. As we are in a group, we can the operation is associative, and so we can group the terms any way we like. And so we have identity star A, or rather star x, is A inverse star B, or more simply, x is A inverse star B. Now since A star, the quantity, A inverse star B, is the same as A star A inverse, the quantity, A star A inverse star B, which is identity star B, which is B. The solution, or rather x equals A inverse star B, is a solution of the equation. So now we need to demonstrate that this solution is unique. So suppose that x sub 1 and x sub 2 are both solutions of the equation A star x equals B. Then A star x sub 1 is equal to B, and A star x sub 2 is equal to B. And so A star x sub 1 is equal to A star x sub 2. And since we are in a group, the left and right cancellation laws hold, and so x sub 1 is equal to x sub 2, and therefore the solution is unique. So second statement, y star A is equal to B. Again, the element A is in the group, and so there exists an inverse for that element. And so we can perform the operation star on the right with that element. As we are in a group, we can, the operation is associative, and so we can group the terms any way we like. And so we have y star identity is B star A inverse, or more simply, y is B star A inverse. Now since the quantity B star A inverse star A is the same as B star the quantity A inverse star A, which is B star identity, which is B, y equals B star A inverse is a solution of the equation y star A is equal to B. So next we need to show that this solution is unique. So suppose that y sub 1 and y sub 2 are both solutions of the equation y star A equals B. Then y sub 1 star A is equal to B, and y sub 2 star A is equal to B. And so we have y sub 1 star A is equal to y sub 2 star A. And since we are in a group, the left and right cancellation laws hold, and so y sub 1 is equal to y sub 2, and hence y equals B star A inverse is a unique solution. All right, so let's look at an example. Let the structure consisting of G with the operation star be a group. And let the elements A, B, and C be in the group. Solve the equation. Quantity A star B star X equals C. So as we are in a group, each element has an inverse, and that includes the quantity a star b. And so we can multiply, or rather perform the operation with the inverse of the quantity a star b on the left on both sides. And again, as we are in a group, we can the operation is associative, and so we can group the terms any way we like. And so we have identity star x is quantity b inverse star a inverse star c, or more simply, x is b inverse star a inverse star c. All right? So next, we'll show that the integer multiples of a given integer n under addition is an abelian group for every choice of integer n. So proof. We have already demonstrated that the integers under addition is a monoid. Now, for every integer a, there exists an additive inverse, namely the opposite of a, or minus a, in the set of integers, such that a plus the opposite of a is equal to the opposite of a plus a, which is 0, where 0 is the additive identity. And so the integers under addition is a group now for every pair of integers a and b. When we perform the product, it does not matter the order in which we take the elements. Whoops. We're in an additive group. When we perform the sum, it does not matter the order in which we take the elements. They are the sum is always the same. And so the group consisting of the integers under addition is abelian. So as the integers under addition is an abelian group, and the integers is isomorphic to the integer multiples of a given integer n for any choice of that integer n, the structure consisting of the integer multiples of that integer n together with addition is an abelian group. For every choice of integer n. All right? So as an example, notice that the equation x plus a equals b, where a and b are integers, has a unique solution. In the set of integers, x plus a is equal to b. As the integers under addition is a group, each element has an inverse, and so we can add the inverse of the element a on both sides. And as we are in a group, the operation is associative, and so we can regroup the terms any way we like. And so we have x plus 0 is equal to b plus the opposite of a, or more simply, x is equal to b plus the opposite of a. Now, as each element in the set of integers under addition has an inverse, subtraction is defined, and so we could state this as b minus a. All right. Now the situation changes for the integers under multiplication. The integer multiples of a given integer n under multiplication is a semigroup, but is not a monoid for n not equal to 1. So proof. Let A and B be in the set nz. Then A is equal to n times x, and B is equal to n times y, where x and y are integers. So the product, A times B, is n times n x y, where n times x times y is an integer. So the product is in the set nz, and hence the structure nz under multiplication is a magma. Now for every 3 elements, A, B, and C, in the set, does not matter how we group the terms, we will always obtain the same result when we take their product. And so the structure nz under multiplication is a semigroup. Now, if n is not equal to 1, then the number 1 is not in the set nz, and so the structure nz is not a monoid if n is not equal to 1. So next we will show that the integers under multiplication is a monoid, but is not a group. So we have just demonstrated, so proof, that the integers under multiplication is a semigroup. Now there does exist the number 1 in the set of integers, such that for every other integer, 1 times a is equal to a times 1, which is a. And so the integers under multiplication is a monoid. However, notice that there exists the number 0 in the set of integers, and there does not exist an integer such that 0 times a is equal to a times 0, which equals 1. Since for every integer, indeed for every real number, 0 or any complex number, 0 times a is equal to a times 0, which is 0, never equal to 1. So the structure consisting of the integers under multiplication is not a group.